I noticed some confusion when we were doing the sampling experiment data workup, so I figured a video of how I organize the data might be useful. I'm going to assume that you know what we did in class and that you did not have any problems in actually collecting the data. If you did, then you probably need to come visit me during office hours or schedule some appointment meeting time. In this workbook, I have 4 worksheets. The raw worksheet looks very similar to what you might have done on your own for tables 1 and 2. We'll come back to that in just a minute. Table A is how I've organized the first table that belongs in your laboratory report. I call it A because I don't want to confuse you with table numbers 1 and 2 from the handout. You should number your tables in your laboratory report sequentially starting from 1, but I wanted to avoid some confusion there. Table B has all of the information that I'm going to need for the second table in the laboratory report. Then I've got this tab called Actual, and this is where I put the information about the actual sample that I collected. And I'll show you why I put this on a separate page in just a few minutes. I think it helps to organize things just a little bit more. I will click on cells that have formulas in them. And if you're following along, you can pause the video, zoom in, take a look at what the formula is, and copy it to try it on your own. So my sample had 2,229 soil beads and so on and so forth, a total of 3,400 beads. For the parts per 100, I took the fraction of beads and multiplied it by 100 to get the parts per 100. And then P, which is needed later on, is just the probability of picking a single component bead. And that's simply the fraction of beads. So this is the amount of beads divided by the total. Now if you take a notice here, I've got dollar signs in my formulas, and just in case you don't know what the dollar signs do, allow me to delete some of these here. If I don't have dollar signs, then if I copy this formula down by clicking on the right-hand corner, I get errors, and that's because I want to always divide by B7, but as I move down, Excel thought that I wanted to move this cell as well, and it keeps moving it down. So I want to actually just move the numerator and not the denominator. By putting in the dollar signs, it allows me to click and drag a formula, and so I don't have to worry about the B7 moving. That stays constant. So dollar signs equals constants in Excel. Okay, let's take a look at the raw data set. And I've got the first table broken up into 2 sets, 2 subtables. Here is all of my data for the small sample sizes, and here's all of my data for the large sample sizes. They're calculated the same exact way, so I will only be talking about one of them, assuming that you know how to transpose to the other table. These numbers are the actual counts of beads that I observed in the 4 different trials. These numbers are the counts converted into parts per 100, and again we're taking the value, the number of beads divided by the total number of beads. Again, I've got a dollar sign in there to keep some of the values constant to make it easy to cut and paste, and then multiply by 100 to convert it into a parts per 100. Average is simply the average command, and then comma separated each one of the parts per 100 that I want to take an average of. And then the standard deviation uses the same format. I want to take the standard deviation of the 4 samples, and this is a sample as opposed to a population standard deviation. So current versions of Excel want stdev.s. If you just type in stdev without the .s, it will work just fine as well. For the second table, we need to look at errors. And again, the second table is split into the small components and the large components. This actually should say large, so I will type that in right now. And let's look at how I calculated these values. For experiment 1, these are absolute errors, and absolute errors are the measured value divided by the actual value. The measured value, if I just type in an equal sign and then scroll up, the actual value is this, the parts per 100, C3. And then notice this new formula right here. The name of the tab where I have the actual values is called actual. And then I have an exclamation point, and so that indicates that I want the value in cell C2 from the actual tab. That allows me to organize my data a little bit more neatly. If you don't want to do that, if you want to keep your actual data over on one part of the spreadsheet, that is fine. This is just one way I think is easy to organize the results. Notice how I can just type in an equal sign and then type in click. Then I can navigate over with my mouse to actual and click here. Oops. Let's try that one more time. Click, then actually hit a minus sign so that it knows, and click, and then press enter, and it figures it out. It figures out the formula just fine. Since this is on the same raw tab, raw exclamation point is not necessary. That's because I just made that little typo. Then I'm going to do that for each one of the absolute errors, just so that you can see the formulas. And then the average is the average of this array. Since all of these are connected to one another, I can use the abbreviated array format, which is B21:E21. And then for the relative error is the absolute error divided by the actual value times 100. So this is percent relative error. And again, I take advantage of the real values being on the actual tab. Multiply by 100, and I get my individual relative errors. Average, just like before. Table 2 small and large, they work the same way. These are the raw data that should not show up in your laboratory report. Some of this information gets put into the new table, so let's take a look at how that happened. If I go over to table A, this table is very close to how I would like you to format your table. We've got small and large results, the average parts per 100 of each component, the standard deviation, the absolute error, and the percent relative error. So these would be the average values. Let's take a look at what I did right here. Notice how there's nothing that's been typed in or recalculated on this page because everything has been calculated on the raw page. So I'm just going to go and find that corresponding value. Soil, the average soil ppH is in raw J3. So let's go over here, raw J3. 3. There it is right there. Excellent. And the standard deviation is in raw K3. So then I go over here just to check, and there it is, K3. All of these values are in the corresponding values in the raw page, raw J4, J5, J6, J7, so on and so forth. Absolute errors, these are the averages, and they're found in, this one is found in F21. So that's this column right here. Then we see that the relative errors, percent relative errors, 3.8 to 165%, are in column K. So you can see how making use of multiple tabs makes it a little bit more convenient to organize our results. It's a tool, you can use that. Now, there was some confusion about what we do and how we present this, what we're going to do with this information. Here are some of the questions that we are trying to answer based on these results. How does the average error, both the absolute error and the percent relative error, compare to the errors observed for a single measurement? So notice how our absolute values here range from a minus 3.8 to a large value of 2.5 in my particular case. So then I go over and look at one of the raw data tables. I believe in our handout I recommended experiment 3. So let's look at experiment 3. And I see the absolute values for the small range from a minus 10 to a plus 4. So this range of values is a little bit larger than the average values that were observed. So it looks like averaging decreases the range of possible errors that we could see. That's one conclusion that I might be able to draw from my data. Your mileage may vary. Second question, how do the average errors for the small sample size compare to the large sample size? So let's look at the average small and the average large for the absolute errors. And when I look at these two values, sets of values, I see a large range here, again minus 3.8 to plus 2.5, minus 2.3 to 1.5, so the range is a little bit smaller. But I look at these sets of values and I see they're kind of close to one another. So there may not be a significant difference between the absolute errors. If I look at the relative errors, though, where for the small values range from minus 34 to 165%, and then the large set ranges from minus 28 to plus 13%, I see that the relative errors are smaller for the large data set. And this is one of the things that's the take-home messages of the sampling experiment. Again, if this is what you observe in your experiment, you can write that down. If you don't see that, that doesn't mean you did it wrong. You need to be honest about the data and say that in this particular case, while you expected the large data set to give you smaller percent relative errors, it didn't turn out. Last question, which representation of error is most affected by the component concentration? I think I just spoke to that a little bit, where we see that the absolute error in my case doesn't seem to have a significant change when we go from the high concentration stuff, such as the soil, to the low concentration stuff. I don't see a particular trend here. However, if I look at the percent relative error, let's look at the absolute values. We go from a small absolute value, 15, 34, 62, 165. I see a trend. Do we see a trend here? Maybe if we squint and ignore lead, we see a 3.5, 5, 13, I ignore that, 28. It's possible that I see trends where the percent relative error increases with a decrease in the concentration, because I know that soil was the most concentrated component in this and dioxin was the last. Again, check to see if you observe these types of phenomena in your data and report out as appropriate. Lastly, this is the table that you are designing on your own, and I've calculated some of the values, but I haven't formatted them into a nice table. I want to spend a little bit of time making sure that you understand how to make these calculations because there were some confusions. First off, when we're calculating the sampling constants. In the sampling constants, the equation is m, or the mass or the sample, or in our case the number of beads, times the relative standard deviation. It's going to be the mass of the entire sample, so that means it's going to be the same for all components. And I took the average mass, or the average number of samples. Again, I calculated this from the raw data. I'll leave that up there so that you can see and work back on your own. And so in my case, the small sample size was around 18 pieces, and the large sample size was approximately 174 pieces. So I take the small value, and let's take a look at how I calculate my sampling constant for small. First off, I do take that 18.5, so that's my B10, and I need the relative standard deviation. That's this right here. Now let's see, so that's K3, J3 on the raw table. K3, and J3. So here, notice how I don't have the RSD actually calculated. And I could, if I wanted to, type in a %RSD and calculate that formula here. If you would like to do that, feel free to do so. I just calculated it on the fly by taking the standard deviation, dividing it by the average of the value, and then notice I multiplied it by 100. And remember that the sampling constant wants that squared. So you use the caret key to raise to the power of 2. And we get that value. I'll leave the formula up for soil for the KS large, just for an example while I talk, and look at the values that I observed. And the question is, do these values look the same or not? I see 2.4 times 10 to the 5th and 9.5 times 10 to the 5th for dioxin. Those don't look too much the same. 1.9 and 2.5 times 10 to the 5th. The lead looks pretty similar. The chlorine is off by a factor of 10. So is the iron. They're different by a factor of 10 in the opposite. In the opposite direction. And soil is not very good either. So in my particular case, the KS does not seem to be a very good indicator of the relationship between sample size and relative standard deviation. If we take a look at our book, we see that part of the reason may be the assumptions that are made with the KS. We do have to assume that there are only 2 types of particles, and that's not really the case. We've got 1, 2, 3, 4, 5 different particles in ours. So it's possible that has an effect. Or it's possible that the sample was not well mixed. And I think several of us have had this conversation about the samples not being as well mixed as they could be, and it could give rise to erroneous KSs. The conclusion that we draw from this analysis is that our sampling procedure needs to be revisited if we were taking this experiment seriously. Okay. The second component that I wanted you to calculate here is the theoretical standard deviation. And that is in our textbook in Chapter 7, and that is equation 7.5. Nope, I lied. That's equation 7.3 in our textbook. And here's how I calculated it for the small and the large values. It's the square root of the number of samples. And notice here it's the number of samples in the sample size. So again, I took the small value of the average of the small sample, and for the large, I took the average of the large sample. Then we need our p-values, so it's p times 1 minus p, and that's how I calculated it in my worksheet. Again, I'm taking advantage of the fact that I have a separate tab with the actual values in it, to make this a little bit easier to write. So I get these numbers here, and at first glance, these numbers don't make a tremendous amount of sense. These are absolute errors, and it looks to me like the error is large for soil and small for dioxin. Furthermore, it looks like the errors are better for the small sample than they are for the large sample. So this is very counterintuitive. And part of the reason for that is that when we think about errors being large or small, they are large or small relative to something else. And if we take a closer look at our textbook, so there's an unnumbered equation in between 7.3 and 7.4 that shows us how to calculate the relative theoretical standard deviation that is theoretically developed. And so we need to take these values and divide by, these are our absolutes, we need to divide by the actual, and that's what I have done right here. Where did I do that? Yep, here we are. So the first thing we do is we take the absolute error, that's this cell right here, divide by the number of samples, and divide by the probability. So what I've essentially done here, let me pull up a quick little text box. The denominator is NP. N is the number of samples, so that's this right here, and then P is the probability of finding that particular sample component. I use divided by signs in here. I could have just as easily done this, and perhaps I should have, to avoid confusion. So this is what I had written and what I've written here are exactly the same. My N and my P. Oops. Yep, there's my P. Just wanted to make sure. Went over here. I noticed here they said B10 divided by actual D2, so I'm going over to actual D2. That is in fact the probability, so I think I'm all set here. Okay, so we've got the KS, we've got the relative standard deviations. We saw the absolute variations don't make a tremendous amount of sense, but in my particular case, if I look at the standard deviations that I observed versus the theoretical values, I'll keep the equation up there for you to compare. I see that these numbers are much, much closer. They are making the trend make sense, where the errors are greater for the lower concentration values, and the errors are less for the larger sample. So it's important that we get to this stage of the data analysis to confirm whether or not our data match the theoretical expectations. Last is the estimating the number of samples needed in order to reach a standard deviation target of 10. Now I'd like you to do something just a little bit different here than I wrote explicitly in the laboratory handout. I'm interested in you determining the number of samples needed just for dioxin. So you don't need to do this for all of them. One of the reasons for that is that the target is 10%, and look at where we are for soil. So you would not need any more samples in order to reach targets of 10%. And in fact, we need smaller samples than the 174 that I used to get to that 10%, because we've already beat it. So this calculation takes a little bit of time to work through, so I'm happy with you just doing this for the dioxin. I'm going to do the example for chloride, just so I can give you an idea of how to do it, but I don't actually give you an answer. As I mentioned in the pre-lab material, this is equation 7.7 in our handout, or in our textbook, and example 7.8 in our textbook goes through this in a little bit more detail. It involves solving equation 7.7 in an iterative fashion. And that's because we know that the value of n is related to the value of t in that equation. So I'm going to look over for the small sample here. This first is the value of t that I can obtain from Excel using TINV. 0.05 is 95% probability, so 1 minus 95%. L4 is the degrees of freedom. Now, Excel doesn't allow me to put in an infinite degrees of freedom, but 1 times 10 to the 10th is pretty darn close to infinite, and that gives me the t value to start with. Once I've got the t inverse, I multiply that by the theoretical standard deviation, divide it by my target standard deviation, and square it. I get a value that's 171 in this case here. I actually take that value, round it, so I've got an integer. And then I need to do this again. So then I do the same exact equation, only this time instead of using a t value for n of 1 million of 1 times 10 to the 10, I'm using it for 171. Notice how the M4 is here. And I get a slightly different value. And I take that value and I plug it in again. 173. I see that. I calculate that t inverse, again H5 and B12, square it, and notice how I get the same value several times, 173, 173. So that tells me my iterative process has converged on a single value. What this tells me is that I would need to do the small sample experiment 173 times in order to improve the standard deviation from 67% to 10%. You did it 4 times. You would need to do it another 169 times in order to get this type of error. Is that practical? That's the question that you're going to need to answer for the dioxin. I did the same thing here for the large sample, and notice how I start off and same idea, start off with 1 times 10 to the 10. Instead now I'm using the theoretical values for the large sample. My target is still 10%. And iterate 3 times. I finally converge on needing to do 20 samples. Still, that's an awful lot of sampling in order to get down to this particular target. What this exercise tells you is whether or not the error or uncertainty that you're looking for is at all reasonable. If you came to me and said, I want, or my boss came to me and said, I want 10% errors or uncertainties in your measurements, you could go back and tell your boss and say, it takes 173 times to do this. That's going to be a week's worth of work. Do you really want to invest that much time of my time in doing this type of measurement? So hopefully that helps out a little bit. I would like you to do this again just for the dioxin and include that information in your laboratory report. Please review this, review your textbook, and if you have any problems, please send me an email and let's try to get things taken care of.